Hi everyone! In this video, we're going to look at 20 integrals that require u-substitution, a fundamental technique in calculus. I've broken these 20 questions down into 3 various levels of difficulty and have provided step-by-step solutions to each. And my hope is that by the end of this video, you will have grown your confidence in tackling integrals requiring u-substitution. Let's get started. So in question number 1, we want to find the integral of x squared plus 3 squared times 2x dx. And this integral requires u-substitution. A common place that we can find our u is inside parentheses, and it's going to be that type of problem. So my u I am going to define as x squared plus 3. What is inside of parentheses? The next thing we need to do is take the derivative of u with respect to x. So du dx would equal 2x. And then I love these questions because it reminds me of a puzzle. You know, you're putting together your u and your du to write a new integral just with u. That's our goal, to write a simple integral only using the variable u. So as I set up my new integral, I know that this x squared plus 3, that quantity, is what I defined as u. So I can swap this out with u squared. Next, I see what I have remaining. I have 2x dx remaining, and I need to substitute that for something with a u. And I can see if I just multiply the dx over, I see that du is equal to 2x dx, a perfect match. So my new integral in terms of u is going to be u squared du. The next step is to integrate. So now we will incorporate strategies of antiderivatives. And in this case, we have a power. We have u to the second power. And to go over the integration strategy when you have a power, the rule is that if you have u to the n du, the antiderivative is u to the power of n plus 1 over n plus 1, provided that n is not equal to negative 1. And in this case, our exponent is 2. So our antiderivative is going to be u to the third over 3. And I wore my t-shirt especially for today. Don't forget that plus c whenever you are finding an indefinite integral. So let's include our plus c, and then our final answer substitutes back in our x squared plus 3 for our u. And my final answer then will be x squared plus 3 cubed all over 3 plus c. And I do know that there are various ways that you can write this final answer. Some may write a 1/3 out in front and then have x squared plus 3 cubed. All right, moving on to number 2. So in number 2, we have some trigonometric functions in here. So in this one common place you could find your u is underneath a radical. And in this problem, that's what I'm going to make as our u. For our u, I'm going to define u as the tangent of x. And so I know I'm going to replace this tangent x with u. And then let's take the derivative of u with respect to x. And the derivative of u with respect to x is the derivative of tangent x, which is secant squared x. And this is great because I find a perfect match right there that du would be equal to secant squared x dx, and I can swap out the secant squared x dx for du. Writing my new integral in terms of u, I'm going to have the square root of u du. And it's time to integrate. With a little rewriting strategy, rewriting this as u to the 1/2 du, I can use the power rule for integrals. I'm going to add 1 to the exponent and divide by that new exponent. So adding 1 to the exponent, 1/2 times 1 gives me u to the 3/2, and then I'm going to divide by the 3/2, and then of course your plus c. We're going to substitute back in our u, and then also, instead of dividing by 3/2, I'm going to multiply by the reciprocal to give a final answer of 2/3 times tangent of x to the power of 3/2 plus c. And some of you may want to rewrite this as 2/3 times the tangent to the power of 3/2 of x plus c. And this is my final answer. So far we have found our u underneath a radical and then also inside of parentheses. Let's take a look at example 3. I'm going to use the strategy where our u is going to be what is inside of those parentheses or inside those grouping symbols. So let's define our u as 2x cubed plus 5 so that I know this whole expression right here is going to be u. Next, let's take the derivative of u with respect to x. And we would get 6x squared. And it looks like after I replace 2x cubed plus 5 with u, it looks like what I have left over is x squared dx. Now, I know some people do u-substitution in a variety of ways, and the way that I like to do it is almost like a puzzle. I'm trying to take my derivative of u with respect to x and form what's left over, and what's left over is x squared dx. And I can form that if I multiply over the dx and divide by the 6. So then I would have 1/6 du is equal to x squared dx. And I can see my match. So in purple, I will be able to replace x squared dx with 1/6 du. So let's go ahead and rewrite this integral all in terms of u. That 1/6 constant, I like to bring that constant out in front of the radical. And then we would have u to the 4th du, and there is my simplified integral written with only the u variable. Now I can take the antiderivative and I would use the power rule for integrals by adding 1 to the exponent and dividing. So my antiderivative would be 1/6 times u to the 5th power over 5, and then don't forget your plus c. So substituting in back our 2x cubed plus 5 for u, let's see, I could write this as 1 over 30 times the quantity of 2x cubed plus 5, all to the 5th power, and then plus c. And that is how you would find this integral. Number 4, I have the integral of x divided by the square root of 5x squared minus 3 dx. And a common place you can find as your u for u-substitution is going to be the expression underneath the radical. So for this problem, I am going to define the u as 5x squared minus 3. So what is underneath the radical right there? I'm going to replace that with a u. Now what I have left over is I have an x times a dx. So that's going to be requiring us to take the derivative of u with respect to x. So du dx is going to be equal to 10x. And what I circled in purple, I can kind of think of those as my leftovers that I need to substitute with the variable u and take out x. So I can see that if I wanted to form x dx with my derivative, I would need to multiply the dx over and divide by the 10. So I can write 1/10 du is going to be equal to x dx. So what is in purple there, the x dx, I can replace with 1/10 du. And so now my integral only in terms of u would be, well, that 1/10 constant I'm going to bring out in front of the integral, and then I would have 1 divided by the square root of u du. And now it's time to integrate this much simpler integral now with 1 over the square root of u. I'm going to do a quick rewrite. I'm going to rewrite this integral as u to the negative 1/2. That is an equivalent form so that I can now use the power rule for integrals, which is to add 1 to the exponent and divide by that new exponent. So my antiderivative would be 1/10 times u to the power of 1/2 because I'm going to add 1 to that exponent and then divide by that exponent, and then don't forget that plus c. So in this case, I'm going to do some simplifying, and instead of dividing by 1/2, I'm going to multiply by the reciprocal. So I'm going to have 1 over 10 times 2 over 1, and then u to the 1/2 power. So that's going to be 5x squared minus 3 to the 1/2 power if I substitute my u back in. And with a little simplifying here, this would simplify to 1/5. And look at this, I can put it back into a radical form as 5x squared minus 3 under the radical, and then plus c. And that's how you would find this integral using u-substitution. In this question, I see some trigonometric functions, and the only way to find this integral is to use u-substitution. And oftentimes where you can find your u is what is inside of parentheses, and that's what I'm going to make as my u this time. I'm going to define my u as x to the power of 3. So whenever I see an x to the power of 3, I know I'm going to replace this with u. Now let's go ahead and take the derivative of u with respect to x. So du dx is going to be equal to 3x squared. Let me see what else I have in this integral. After I change the x cubes to u, it looks like I still have an x here that needs to be replaced and a dx here that needs to be replaced. And looking at my derivative in blue, I want to try to form x squared dx. So I can substitute the variables u back in. And I can form that if I divide by 3 and I multiply over the dx. And there we go, x squared dx. I can replace that with 1/3 du. Let's go ahead and rewrite this integral only in terms of u. That 1/3 constant I'm going to bring out in front. And then let's see, I would have secant u, tangent u, and then du. And this is much simpler now to integrate because one of our integrals, actually in fact one of our trig integrals, if you have secant u, tangent u, du, the antiderivative is secant u, not the d. Let's try that again. Secant u plus c. So using that trig integral, I'm going to rewrite this as 1/3 secant of u plus c, and substituting my u back in, I would have 1/3 secant of x cubed plus c. And there is my answer to this integral using u-substitution. All right, I consider, again, all of these integrals that I'm doing right now, I consider them all level 1. So stick around where you can see a little bit more challenging integrals in level 2 and level 3. So in this problem, well, oftentimes we make what's inside the trig function our u, which some people may think is 3x, but in this problem, the u is actually not 3x. If you think about this being rewritten as sine of 3x squared times cosine 3x dx, it's actually not the 3x that I'm going to make as my u. I'm going to make what's inside of parentheses my u. So I'm going to make the sine of 3x the u variable. So I'm going to substitute sine of 3x for u. Taking the derivative of u with respect to x, I would have cosine 3x, and then we would need to use the chain rule, so times 3. And let's see, if I replace sine of 3x with u, what's remaining is cosine 3x dx. And I can use some, let's see, a little algebra here, divide by the 3, multiply over the dx to see what I'm going to replace cosine 3x dx with, and that's going to be replaced with 1/3 du. So let's rewrite this integral with only our u variable. I'm going to bring that constant of 1/3 out in front. Sine of 3x squared now becomes u squared. And then I would just have du. And look at that. That is a much simpler integral that I can use antiderivative strategies to find this integral. And if I take the antiderivative of u squared, I would add 1 and divide by that same number, and then add your plus c. Substituting back in your u, I would have, and there's different ways to rewrite this, but you can rewrite it as 1/9 times sine of 3x to the 3rd power plus c, or you can even write it as, for example, sine cubed of 3x over 9 plus c, whichever way you prefer. I think they're both good answers to leave it like that. And now on to question number 7. Just a reminder that if you look in the description below, I have provided a link to all of these questions so that you can follow along or even pause the video and try one on your own before I show it. All right, so in number 7, we have the integral of e to the power of 1 over x squared dx. And we've talked about where you can find your u in terms of inside parentheses or under a radical. Well, sometimes you may find your u as an exponent, and that's the case for number 7. So here I'm going to write my u as 1 over x. So I'm going to make the exponent be the u. So I will substitute in 1 over x for u. The next thing I need to do is I want to find the derivative of u with respect to x. And I'm going to do that by rewriting this as x to the power of -1 so that I can use the power rule for derivatives. So the power rule would give me a derivative of -1. X to the -2 or -1 over x squared. And as I look at my problem, if I make it e to the power of u, what I have left over is I have an x squared in the denominator and I have a dx here. Now I know people do u-substitution in various ways. What I like to do is I like to look over at my derivative and I want to try to form what I circled in purple. And I almost have it except for this negative sign right there. So I'm going to divide the negative sign over and multiply the dx over. So I would have negative du is equal to 1 over x squared dx. And then I do have what I have in purple, and I can replace what I have in purple with negative du. So my new integral, written only in terms of u, would be, well, I would have e to the power of u and then a negative du, but I'm going to put the negative sign out in front and then the du inside the integral. And look at that. That is a much simpler integral. All I have to do is take the antiderivative of e to the u. And that's my favorite one. It's e to the u. So the antiderivative would be negative e to the u. And of course, don't forget the plus c. And then the last step would be to just replace the u with our 1 over x. So negative e to the power of 1 over x plus c is my final answer. So just remember, another place you could find your u is in an exponent. And that's going to be the case with problem number 8. So I'm going to make the u be the exponent of cosine x. So think about that. I'm going to replace this cosine x with u. So I will have 3 to the power of u in that part. But look what's left over. I have this sine of x and dx left over. And the only way I can replace that is if I take the derivative of u with respect to x. So over here, the derivative of u with respect to x is going to be the derivative of cosine, which is negative sine of x. Well, what I circled in purple is a positive sine of x dx, but I can quickly get that if I just divide by the -1 and multiply over the dx. So I would have negative du equals sine of x dx, and I can replace the sine x dx with, this would combine to negative du. Let's go ahead and rewrite this integral in terms of u. And that negative sign in front of the du, I'm going to bring out in front of the integral. And then let's see, we would have 3 to the power of u du, a much simpler integral than what we started with. And that's the power of u-substitution. We're using u-substitution to write it in a much simpler way. And now it's time to take this antiderivative. Let me go over this antiderivative shortcut rule. So if you have the integral of a to the power of u du, your antiderivative would be 1 over the natural log of a times a to the power of u plus c. So I'll go ahead and use that strategy in this problem. I would have negative 1 over the natural log of 3 times 3 to the power of u, and of course our constant. Add that constant in. And I know you can simplify this in various ways, but we want to make sure to substitute in that u for cosine x at the very least. So we could write it as negative 3 to the power of cosine x over the natural log of 3 plus c. And there is your answer to this integral. So oftentimes, remember, you may make that exponent your u. Let's take a look at number 9. All right, number 9 is a different one. We haven't seen this one yet. So there are no parentheses, so I can't make my u be what's in parentheses, or there's no radicals, so I can't make my u be what's inside the radical, and there's no exponents that have an x. So in this problem, I am going to incorporate a new strategy, which is to make the denominator be the u. Now, what made me think of this? It's because if I set the denominator as my u and take the derivative, well, my u is a cubic, and if I take the derivative of a cubic, I get a quadratic, and that's what I have in the numerator, and that's going to be helpful. So here, the u is going to be 5 minus x cubed, and that is what I'm going to replace this with, the u, but then I've got this x squared and this dx left over. Well, I'm going to get that by finding the derivative of u with respect to x. So this is going to be du dx is equal to, and the derivative here would be negative 3x squared. And remember, what I circled in purple was x squared dx. So here's time for the puzzle part of it. The reason I love u-substitution is I have to take what I wrote in blue and see if I can form x squared dx. And I can do that if I multiply the dx over, but divide by that negative 3. So I will have negative 1/3 du equals x squared dx, and that is what I can replace what I circled over here in purple. I can replace this with a negative 1/3 du. Now let's rewrite our integral with only the variable u. Well, that negative 1/3 constant that's being multiplied by du, I'm going to bring that constant out here in front. And let's see, I would have 1/u times du. And again, a much simpler integral, and that's the power of u-substitution. But now I need to take the antiderivative of 1/u. And in fact, this one is not one I can use the power rule for integrals for. And some people think, oh, I can rewrite the 1/u as u to the negative 1, for instance. Well, if you try to add 1 and divide, you would get u to the power of 0 over 0. Yeah, doesn't work like that. So you need to then recall what is the antiderivative of 1/u, and that is the natural log of the absolute value of u. So here the antiderivative would be negative 1/3 times the natural log of the absolute value of u, and don't forget that plus c. Let's substitute back in the expression 5 minus x cubed for our u to get a final answer of negative 1/3 times the natural log of 5 minus x cubed plus c. And there is our answer to this problem number 9. So notice we've used now a new strategy, and this strategy is make the denominator your u. All right, looking at number 10, and I hope by going through these, I hope your understanding of u-substitution is just growing and growing, and your confidence is growing right along with it. All right, in number 10, I am finding the integral of secant squared x divided by tangent x dx. And some people may wonder, what should I make as the u? Would I make the u secant x? Would I make the u tangent x? And there are some various ways that people think about it, but you know what I think about? If I were to make the u be secant x, well, the derivative would be secant x tangent x. But if I were to make the u tangent x, my derivative would be secant squared x. And I like that one. So I'm going to use the strategy where we make the denominator be our u. So u is going to be tangent of x, so that's what I will replace the u with. And then du dx is going to be secant squared x. And that is exactly what I have here. I have a secant squared x, and then I also have a dx. Well, I can form that with my derivative if I simply multiply the dx over. So du is going to be secant squared x dx. And so I can replace what I circled there in purple simply with du. And look at this new integral written in terms of u. We have a simple 1 divided by u du. So much simpler than the integral that we started with. So now we just need to take the antiderivative of 1/u, and that's going to be natural log of the absolute value of u. So let's go ahead and write that out. And of course, with your plus c, and then let's swap back in the u of tangent x. And we would have the natural log of the absolute value of tangent of x plus c. And that is the answer to that integral. All right, I'm still calling these integrals level 1. I think I've got 13 questions that I put into level 1, and then we'll jump to level 2, even harder questions. All right, in this integral, we have the integral of dx over the square root of 4 minus x squared. Now, oftentimes I make what is underneath the radical the u. But I'm going to show you why that's actually not going to be the u for this problem. And I'm going to put this in red to remind us we are not going to use this method actually. So like I said, oftentimes we would make what's underneath the radical be our u. But when you take the derivative of u with respect to x, I would get negative 2x. And so if I replaced this with u, well, I've got this x that shows up when I take the derivative. And I don't see any x here in my problem. And that's how I know that I'm not going to make what is underneath the radical the u. So this method, not going to be the method that I'm going to go with. In fact, this one is actually going to be what we call an inverse trig problem. All right, this is actually going to be an integral that produces an arc sine function. And let me go through what that integral rule looks like. So if you have the integral of, for example, let's use du divided by the square root of a squared minus u squared, that is going to equal arc sine of u over a plus c. And I can see that this problem has that form. And we already tried to make what's underneath the radical our u, and we found that that did not work. Well, can I form what I am given with that integral that I wrote over there with the a's and the u's? And I actually can. So if I make the a be equal to 2 and the u be equal to x, I can rewrite this integral. So then I would have the integral of, let's see, well, first, I'm going to erase this integral here and find the derivative of u with respect to x, and that's just 1. So du is in fact equal to dx. So what I'm going to do now is I'm going to replace the x with u and the dx with du. And the 4 you can either write as 2 squared, or if you want to write it as a squared, you can do that too. At least we wrote that a is 2 off to the side. So I could rewrite this problem as du over the square root of a squared minus u squared. And that's exactly what the pattern is. If you're finding the integral of an integral that produces an arc sine function. So this would produce, as I wrote over there on the right already, arc sine of u over a plus c. And if I substitute back in ru and ra that we defined, we would have arc sine of x over 2 plus c. So we need to be careful of that one. This is a sneaky little inverse trig integral because it doesn't work to make what is underneath the radical equal to our u. Let's move on to question number 12. And just a reminder, in the description below, I've provided a link where you can print off the PDF of all these problems to follow along. And remember, you can even pause the video and try the questions first before I get started. All right, let's take a look at this integral. We have the integral of 4 divided by 2 plus 9x squared. And I do know that one of the strategies in u-substitution is to make the denominator be your u. And I'm actually going to start with that to show you why that doesn't work here. And I'm going to write it in red so that I can show you that I would then cross it out. So a common strategy is to make the denominator of your fraction be the u. So I would replace all of this with u. And that seems like it would be okay, but then you would have to replace this dx with something involving a u. And so I would have to take the derivative of u with respect to x. I would get 18x. And the issue here is that an x shows up. So that if you solve for dx, you would have something with an x, and that would be an issue because then we would have both u's and x's. So we are not going to use this method where you would make the denominator be your u. So instead, this is a little sneaky one. This is an inverse trig integral. What I mean by that, it's an integral that produces an inverse trig function. And in this case, it's going to produce an arctangent function. So let me show you what the arctangent kind of integral formula is. And if you can write an integral as du over a squared plus u squared, then that integral is going to produce 1 over a arctangent of u over a plus c. And that's going to be what we're going to use here. And to start, I would probably start by factoring that 4 out, or bringing that constant of 4 out in front of the integral. And then in this case, I would have dx, or I can put a 1 here and the dx over here. And then I can rewrite this as the square root of 2 squared plus 3x squared. And now you can see I have written it in the form that would produce an arctangent function. So in this case, a is the square root of 2 and u is 3x. So now when you take the derivative of u with respect to x, you no longer have that x that shows up. You would just have 3. So then I'd be able to solve for dx by dividing by 3 and multiplying over the dx. So I can replace the dx with 1/3 du. So this right here would be replaced with 1/3 du. And now I can rewrite this integral in terms of a and u and give it that form that would produce an arctangent function. So I have the 4 out in front of the integral. Well, I also have this constant 1/3 that I'm going to bring out. So I'm going to have 4 times 1/3 in front of the integral. And then I would have 1 over, well, if I made the root 2 be the a, you can leave it as root 2 squared, or if you wanted to write a squared plus, and then the 3x is my u, so a squared plus u squared, and then du, because that 1/3 I have brought out in front. And now this would be an integral that would produce an arctangent function. So I would have 4/3 times 1 over a arctangent of u over a plus c. Let's plug back in our a and plug back in our u, and you would have 4 over 3 root 2 times arctangent of 3x divided by root 2 plus c. And in this case, I have not rationalized the denominator, but I know some people may want to rationalize that denominator. And in that case, let's see, you would have, I'll write it over here, you'd have 4 root 2 over 3 times 2, which is 6, arctangent of 3x times root 2 over 2 plus c. Totally your preference on how you prefer to write it. So you may see answers of 2 root 2 over 3 arctangent. And there'd be various ways you could rewrite this. Maybe rewrite it as like x times 3 root 2. I don't know, variety of ways. And then plus c to just show you a couple ways you may see it rewritten. All right, so that is an integral that would produce an arctangent function using u-substitution. I have one more question that I have considered a level 1 question, and it's this one. It seems very simple, the integral of tangent x dx. Now, some of you may just memorize what this comes out to be, but I like to show why it comes out to be what some people memorize. So if I see the integral of tangent x dx, I think, how else could I rewrite tangent of x? And I'm going to rewrite this integral as sine of x over cosine of x using that trig identity that tangent x is sine over cosine. And now I can use u-substitution. And one of my u-substitution strategies is to make the denominator be the u. And that's what I'm going to do in this problem. So I'm going to make cosine x be u, so then I can replace this with u. Well, now notice I have this sine of x times dx that I need to replace with something, and I can get that by taking the derivative of u with respect to x. So when I take the derivative of u with respect to x, I get negative sine of x as the derivative of cosine. So I can form positive sine of x dx by dividing the negative 1 over and multiplying the dx over. So I would have negative du equals sine of x dx. So I can replace what I circled there in purple with negative du. So now my new integral in terms of only u is going to be 1 over u, and then I have a negative du, but I'm going to bring the negative out in front and the du here. And you can see I have produced an integral that would give me an antiderivative of natural log of the absolute value of u. So let's go ahead and write it. So I would have negative natural log of the absolute value of u plus c. Plugging in the cosine of x for u, this would produce negative natural log of the absolute value of cosine x plus c. And some people just have that rule memorized, but it's kind of cool to see why the integral of tangent of x is negative natural log of cosine x plus c. All right, everybody, it is time. We are kicking it up a notch. We are going up to level 2. So the following problems are just a bit more challenging, but the more you stick with it, you are going to improve your skills in U-substitution and my hope, your confidence as well. So we're moving on to question number 14. We have the integral of 3x cubed plus 2x plus 5, all divided by x squared plus 4. Now, one U-substitution strategy is to make the denominator be the u. Now, that's not what we're actually going to do in this problem. I'm going to show you what it would come out to be, and I'll write it in red because I'm going to end up erasing this or crossing it out. So a common strategy is to make your denominator be the u. But in this case, it doesn't work because when you take the derivative of u with respect to x, you only get 2x. You don't get anything as a cubic, x cubed, plus 2x plus 5. So we are not going to use the strategy where we make the denominator be the u. And some of you may think, okay, but would I make the numerator be the u? Well, that's not going to work in this case either because we have the x squared plus 4 in the denominator. So you'll never produce that when you take the derivative of u with respect to x. So on our first level 2 questions, we need to rewrite this integral. And the strategy that we're going to use to rewrite this integral is we are going to use long division. So we're actually going to divide these polynomials and then we're going to rewrite it. So how do I know that I would even use this strategy on a problem like this? Like, what's the kind of thing that I see in this problem to know to do that? And I would say if the degree in the numerator is larger than the degree in the denominator, one strategy you may want to try is long division. So if I set up long division here, I would have 3x cubed plus 2x plus 5 divided by x squared plus 4. All right, with long division, I can take 3x cubed and divide it by x squared, and I would get 3x. Let's go ahead and multiply 3x by the quantity x squared plus 4. 3x times x squared would be 3x cubed. 3x times 4 is 12x. And then I would need to subtract this quantity. 3x cubed minus 3x cubed would cancel away, and then 2x minus 12x is going to give us a negative 10x. Let's go ahead and bring down the plus 5. And it looks like my long division process is done because I can't divide negative 10x by x squared and get something without a negative exponent. So with that, I can rewrite this integral as the integral of 3x, because that's what I got when I did the long division. All right, and then this negative 10x plus 5, all of this is my remainder. So I would write the remainder of negative 10x plus 5 divided by x squared plus 4, and then I would have dx. All right, so that is how I would rewrite this problem after I use long division. Okay, so now it's time to integrate this. Well, 3x, that one's not too bad. That's a polynomial. I can use the power rule. I can add 1 to the exponent, and I can divide. But this next one, negative 10x plus 5 over x squared plus 4, that one is a lot more challenging. And you may think, okay, on this one, let's make the denominator be the u, as we've shown over there in red. Make u be x squared plus 4. But then again, when I take the derivative of u with respect to x, I get 2x. But my numerator is negative 10x plus 5, a much more complicated numerator than just 2x. So we're going to incorporate even another strategy in this one. Now you can see why I consider this a level 2 question. What I'm going to do on this one is I am going to rewrite this, all right, but then I am going to split up that fraction. So I'm going to rewrite this as negative 10x over x squared plus 4 and then I'm going to have plus 5 over x squared plus 4, and all of this dx. All right, I'm running into the purple over there. I need some more space. So what I'm going to do now is I'm going to split this into 3 different integrals. And in fact, every single one of these integrals is going to be a different integration strategy. That's why this is a great problem. It's like a 3-in-1 problem. So the first integral is going to be 3x dx. That's going to be our simplest one. And then our next one, we're going to have the integral of negative 10x over x squared plus 4 dx. And then finally the integral of 5 over x squared plus 4 dx. Like I said, all of these are going to have different integration strategies. So let's start with the first one. The integral of 3x dx. Well, I can use the power rule for integrals, and if I write that as an exponent of 1, I'm going to add 1 to the exponent and divide. So 3x squared over 2, and then that one's going to be plus c. All right, let's look at the middle one. In the middle one, I have the integral of negative 10x over x squared plus 4. Now in this integral, this is the one that I'm going to make the denominator be the u. I'm going to set the denominator equal to u. And then my derivative of u with respect to x is going to be 2x. Now I really like that because in the numerator I do have x dx, and I can form that x dx by multiplying over the dx and dividing by 2. Now some people, one strategy I really like is some people may, replace this with a 2 and bring the negative 5 out in front. And I think that's clever too, because then you can replace the 2x dx with du. I might go that strategy actually. Let's do that. Let's have du be 2x dx. And so now I can replace that entire 2x dx with du. So rewriting that middle integral, I would have negative 5 times the integral of, let's see, this would be 1 over u du. Yeah, I think I like this one. So I would have negative 5 times the natural log of the absolute value of u plus c. And plugging back in our u, I would have negative 5 times the natural log of the absolute value of x squared plus 4 plus c. Even though I actually think x squared plus 4 would always be positive, so I guess we could drop the absolute value in this case. All right, and then looking at the third one, here I see the integral of 5 over x squared plus 4. Now this one I can't make the denominator equal to u because it would produce this x when I take the derivative, and I don't have an x in the numerator. So this is going to be one of those sneaky inverse trig integrals, and that's because I don't have an x in the numerator. So this is going to be an integral that produces arctangent, because I can write this integral as 5 times the integral of 1 over a squared plus u squared du if I make the a value be 2 and the u value be x, and du dx is 1 or du is dx. And so using that substitution, you can now see how the integral could be rewritten as what I have put here. All right, so now the antiderivative would be 5 times 1 divided by a arctangent of u over a plus c. And plugging in our u of x and our a of 2, we would have 5 over 2 arctangent of x divided by 2 plus c. And now it's time to write all 3 of these together. So we have this one, we have this one, and we have this one. And guess what a constant plus a constant plus a constant is? A constant. So I'm just going to put a single plus c at the end. So my final answer of this beautiful integral is going to be 3x squared divided by 2 minus 5 times the natural log of the absolute value of x squared plus 4 plus 5 divided by 2 arctangent of x over 2. And then after all that, don't forget your plus c. And there we have it. That is a fun one. I love that one. Think about what we had to do from the very beginning. We had to first start by using long division and then splitting it up into 3 different integrals that all had 3 different integration strategies. And now you can see why I called this a level 2. Let's look at our next level 2 question, and we have the integral of x minus 1 over x plus 1 dx. Now, again, sometimes people's strategy would be to make the denominator the u. Well, in this case, I wouldn't make the denominator be u because then the derivative would just be 1 and I wouldn't get the x minus 1. So on the previous question, we used long division, and I use long division whenever the degree in the numerator is higher than the degree in the denominator, but I also use division when the degree in the numerator is equal to the degree in the denominator, and that's what we have here. So you can use long division again, or you could use synthetic division on this one since the denominator is a linear factor. So you know what? Let's use synthetic division on this one. So as I set up my synthetic division, since I'm dividing by x plus 1, I would put negative 1 there, and the coefficients of my numerator are 1 and negative 1. In long division, we would in synthetic division, we would bring down the 1, multiply 1 times negative 1 and get negative 1, and then add those together and we get negative 2. This allows us to rewrite this integral as 1, and then we have a remainder of negative 2 over x plus 1 dx. And that's the whole point of using division, either long division or synthetic division, so that you can rewrite this integral and then be able to use integration strategies. So now I'm going to split up this integral into 1 dx and then plus the integral of negative 2 over x plus 1 dx. And once again, we have two integrals that require two different integration strategies, which is a great problem in my book. So in the first one, the antiderivative of 1 dx, well, that one's going to be x plus c. And in the next one, negative 2 divided by x plus 1, for this one, we are going to use u-substitution. And I'm going to use the strategy where we make the denominator equal to u. And then when we find the derivative of u with respect to x, I would get 1. And multiplying the dx over, you can see then that I would replace this dx with du. And so that integral can be rewritten by bringing the negative 2 out in front of the integral and then having 1 divided by u du. The antiderivative uses a natural log. So it would be negative 2 times the natural log of u. And replacing our u with the expression x plus 1, you can see that the antiderivative would be negative 2, natural log of the absolute value of x plus 1 plus c. So let's go ahead and rewrite this and this together to get our final answer. And our final answer would be x minus 2 natural log of the absolute value of x plus 1. And then we had a constant plus a constant, so together that gives us one single constant, one single plus c. So that was a good one. We got to use division and then split it into two different integrals, that we got to use two different integration strategies, one of them being u-substitution. All right, let's look at another level 2 question. So in here, we're taking the integral of dx divided by x squared plus 4x plus 13. Now, a common u-substitution approach is to set the denominator equal to the u. Now, that's not going to work in this problem, and I'll show you why. I'll write it in red and then cross it out. So if you set the denominator equal to u, and then you took the derivative of u with respect to x, you would get 2x plus 4. And that doesn't show up anywhere in the problem. So that's how I know I am not going to want to use that strategy in this case. With a denominator as a polynomial and a constant in the numerator, in this case we can think about a constant being 1, I know that this is going to produce an inverse trig function, and it's going to produce an arctangent function. Why? Because I see that it's in the form of an integral of du divided by something that I can put in the form of a squared plus u squared. And then that, like I said, will produce an antiderivative that's going to be arctangent, an arctangent function. Now, this is where, the hard part is producing that a squared plus u squared in the denominator, and that's going to require a strategy called completing the square. I love these problems. There's some really good mathematics in them. So here, if I think about taking x squared plus 4x, I want to complete the square and make this a perfect square trinomial. So I'm going to complete the square right there. Let me move the plus 13 over and add. I like to kind of set up a little blank where I'm going to complete the square. So to complete the square, you are going to take this b value, divide it by 2, and then you are going to take that number and square it. So we get 4. Now we can't just go in and add 4. We have to undo what we just did. So then over here we go in and subtract 4. So the plus 4 and the minus 4 cancel each other out. So now the whole point of completing the square, like I said, is so that I can write that as a perfect square trinomial. So I can rewrite the denominator as x plus 2 squared plus 13 and negative 4 give us 9, which is 3 squared. All right, and we're getting closer to rewriting it as that form in terms of u, and you can do that if you make the a be equal to 3 and the u be equal to x plus 2. Let's take the derivative of u with respect to x. We get 1, so then du is dx, and I can rewrite this integral as what I have just shown above. So dx is du, and then if I kind of switch the order here and think about 3 squared being first, I do have a squared plus u squared, and you can see then that it would produce this arctangent function. So now if I replace, well, let me write it again. This would give us 1 over a arctangent of u over a plus c, and now let's replace the u back in with the x plus 2 and the a with the 3. So my final answer would be 1/3 arctangent of x plus 2 over 3 plus c. This was a great problem. We got to complete the square in this problem and then set it up as an integral that would produce arctangent. All right, let's look at another problem where we would in fact have to complete the square. So it does not work to make what's underneath the radical the u, because if you take the derivative of 2x minus x squared, you would get 2 minus 2x, and I don't see that anywhere in the problem, so I know I'm not going to be able to set what's underneath the radical equal to my u. I'm going to have to take a different approach. And this is going to be an integral that will produce an arcsine function. So let me go through what that integral looks like. So again, if you can create an integral that looks like this, this is going to be equal to arcsine of u over a plus c. I just need to get it to look like that. So it needs to be a constant squared minus something that I'm going to set u equal to squared. And to do this, it will require completing the square. So in this case, I'm going to take what is underneath the radical and I'm going to write it in standard form. And then to complete the square, I am going to factor out the -1. And let's go ahead and complete the square right there inside of the parentheses. So to complete the square, I'm going to take this value right here and divide it by 2. And then we are going to square it. So I get a +1. Now we can't just go in and add 1 randomly without undoing what we just did, because we're not trying to change the problem. And this is where mistakes happen. So it appears as though I've added 1, but have I really added 1? I have not. Because of this -1 out in front, I have actually subtracted 1. So to undo that, I will need to add 1 outside of the parentheses. So rewriting this, I will have -1, and then I can now factor the x squared minus 2x plus 1 as the binomial x minus 1 squared, and then I have +1. And I'm going to switch the order here, and I'm going to start with the 1 and then subtract the x minus 1 squared. That means the exact same thing. The reason I'm going to do that is because now I can make it look like this. I can make it look like here is my a squared, here is my minus u squared, so as long as a is 1 and u is x minus 1, this will work. Du dx is going to be 1, so du is going to be, oops, not 1, but dx. So now I can rewrite this original integral as the integral of, let's see, 1 over, and the square root of 2x minus x squared, we said we can rewrite as 1 minus x minus 1 squared, but if we make a as 1 and u as x minus 1, you can see how I can write this as a squared minus u squared, and then since dx is du, there we go. We have the setup for an integral that would produce an arc-sine function. And now all I have to do is replace my u with x minus 1 and the a with 1 for a final answer of arc-sine of x minus 1 over 1, which is just x minus 1, and then plus c. This is a good one. It had a little bit of a trickier completing the square component to it. And I always think any integral that produces an inverse trig function is just a little bit more challenging, and that's why this was considered a level 2 question. Let's move on to question number 18. In this question, we are going to use the strategy called splitting up the fraction. And what I mean by that is we are going to rewrite this integral as x divided by the denominator plus 2 divided by the denominator. So here we go. Splitting up the fraction gives us x divided by the square root of 4 minus x squared plus 2 over the square root of 4 minus x squared dx. And what we can do, because we've rewritten it as 2 fractions, is that we can actually split it up into 2 separate integrals. So this is going to be the integral of x divided by the square root of 4 minus x squared dx plus the integral of 2 over the square root of 4 minus x squared dx. And this is why I love this problem. We actually get a 2-for-1 deal here. We have 2 different integrals, and we're actually going to solve these integrals in 2 different ways. So looking at the first integral, the strategy that we're going to use for this one is we are going to set what's underneath the radical, so the radicand, equal to our u. So we are going to set u equal to 4 minus x squared, and the derivative of u with respect to x is negative 2x. The reason we're going to use this strategy for this integral is because once I set 4 minus x squared equal to u, what I have left over is x dx, and I can form that using my derivative by multiplying over the dx and dividing over the 2. So I would have negative 1/2 du is equal to x dx, which means what I circled in purple I can replace with negative 1/2 du. And now I am able to rewrite that integral 1 over the square root of u, and then the negative 1/2 I can actually bring in front of the integral and then have the du. Okay, now it's time to integrate this one, and before I integrate, I'm actually going to rewrite this integral as u to the negative 1/2 du. It means the same exact thing, but now I can use the power rule for integrals, which means I'm going to add 1 to that exponent and divide. So then I would have negative 1/2 times u to the 1/2, because I added 1 to negative 1/2, divided by 1/2 plus c. Now to do some simplifying, I'm going to take negative 1/2, and instead of dividing by 1/2, I'm going to multiply by the reciprocal, so that would be times 2 over 1. And then it would be times u to the 1/2, and our u was 4 minus x squared, so that's going to be 4 minus x squared to the power of 1/2 plus c. A little bit of simplifying here, negative 1/2 times 2 will give us a negative 1, and then 4 minus x squared to the 1/2 is the same as the square root of 4 minus x squared plus c. So that's the first integral. We have a second integral over here, and like I said, we're actually going to solve that integral using a completely different method. The reason we can't use the same method as we did on the previous integral is because if we set the radicand equal to u, when we take the derivative, we get this x variable that's nowhere to be found in the second integral. So the second integral is actually going to produce an inverse trig function, and in this case it's going to be arc-sine. So to go over kind of that arc-sine rule, if we are able to write our integral as du divided by the square root of a squared minus u squared, then the integral would produce arc-sine of u over a plus c. And we can write it this way if we make our a value equal to 2, and our u value equal to x, and then we can write it that way. Also, if we take the derivative of u with respect to x, we get 1, or du is equal to dx. So rewriting this integral, and I'm going to go ahead and bring the 2 out in front, we would have du divided by the square root of, and since 4 is our a value of 2 squared, we can write this as a squared minus, and our u variable is the same thing as x, so we can write this as a squared minus u squared under the radical. Like I said, this would produce an arc sine function, so this would be 2 arc sine of u over a plus c. Plugging back in our u as x and our a value is 2, you can see that that would be the antiderivative. So therefore, my final answer, if I combine this answer with this answer, my final answer of this integral is going to be negative square root of 4 minus x squared plus 2 arc sine of x divided by 2, and then because a constant plus a constant is equal to a constant, I can just put a single plus c at the very end. All right, we have gotten to the moment that I've been waiting for, the level 3 questions. I have 2 questions, and I say that they are level 3. In this problem, we're looking at the integral of x times the square root of 2x minus 1 dx. Now, one of our integral strategies with u-substitution is to make what is underneath the square root our value of u. And that's what I'm going to do for this one. I'm going to set u equal to 2x minus 1, and then when I take the derivative of u with respect to x, I would have 2. Now, here's the issue that we run into. This expression, 2x minus 1, is u, and then this dx, I can solve for dx down here by dividing by 2 and multiplying over dx. So I can see then that this I would replace with 1/2 du. But here's our issue. This darn x there, I have to replace with something. It didn't show up when I took the derivative. Well, there's a trick to this. Because we defined u as 2x minus 1, we can take this equation and we can solve it for x. And that's what we can replace x with after our integral. So we can add 1 to this side, and then we can divide both sides by 2. So then you can see x is u plus 1 over 2. So let's rewrite this integral. So we would have the integral of, instead of x, we can replace that with u plus 1 divided by 2. And then we would have times the square root of u. Then we would have times 1/2 du. But that 1/2 constant I am going to bring out in front of the integral, and then I would have du. I mean, this still isn't an easy integral to solve for, so there's still some strategies that we have to use in here, and there are actually going to be some algebraic strategies. Now, this fraction is being divided by 2, so I'm going to bring that out in front of the integral as well, and this I would have as 1/4 times the integral of the quantity u plus 1, and then I'm going to write the square root of u. I'm going to rewrite this as u to the 1/2, because what this problem requires us to do is to distribute in the u to the power of 1/2. Well, at least that's how I would solve it. You'll all probably come up with a much clever way to do this, and I would love to hear about that in the comments. So this I would rewrite as 1/4 times the integral of u to the 3/2 plus u to the 1/2, and then du. And now I can use the power rule for integrals, which means I can add 1 to the exponent and divide. So this would be, I don't know why I just wrote a. Let's try that again. U to the 5/2 divided by 5/2, and then plus u to the 3/2 divided by 3/2, and then plus c. So a couple things I'm going to do now. Instead of dividing by a fraction, I'm going to multiply by the reciprocal and also replace the u with the expression 2x minus 1. So this would be equivalent to 1/4 times 2 divided by 5, and then our u was 2x minus 1, so that'd be 2x minus 1 to the power of 5/2, plus 2 divided by 3 times the quantity 2x minus 1 to the power of 3/2. And of course, don't forget the plus c at the very end whenever you are solving an indefinite integral. Never forget that plus c. All right, everybody, this is it. Question number 20, last one, and I'm hoping by the end you feel much better at U-substitution. So I'd love to hear about that in the comments below. All right, I'm going to do the same thing as I did in the last problem. Oftentimes with U-substitution, we make what is underneath the radical the value of u, and that's what I'm going to do here. Now, the complicated thing is here, when you take the derivative of u with respect to x, you just get 1, or du is equal to dx. So I can replace this dx with du. I can replace the quantity x plus 4 with u, but here's the difficulty. In the numerator, I have the expression 2x plus 1. And I don't see that show up anywhere with my blue numbers as I try to, make this puzzle and plug in something there. So instead, what I need to do is I need to solve this equation for x. So x is going to be equal to u minus 4. And that's what I'm going to replace this x with. And that way I'll be able to write this integral only in terms of u. So let's take a look at what that would be. This would be the integral of 2 times u minus 4 plus 1 over the square root of u du. I've got some algebra strategies I need to use here because we don't know the antiderivative of that. So we need to do some rewriting over here. 2u minus 8 plus 1 over the square root of u du. From here, let's rewrite this as 2u minus 7 over the square root of u. Actually, I'm not going to write that as the square root of u. I'm going to rewrite that as u to the 1/2 since it means the same exact thing. All right, from here, let's use the strategy of splitting up the fraction. So we would have 2u over u to the 1/2 minus 7 over u to the 1/2 du. And let's use some exponent properties here to rewrite this as 2u to the power of 1/2 because we would subtract those exponents. And then this one can be written as minus 7u to the negative 1/2 using our exponent properties du. All right, now we can use the power rule for integrals. We can add 1 and divide. And if it makes you feel better, we can even, do this properly and split up this integral into 2 integrals here. All right, now let's go ahead and add 1 and divide. So this would be 2u to the 3/2 over 3/2. Then I would have a plus constant there, but I'm just going to add a final constant at the end. 7u to the power of positive 1/2 because I would want to add 1 to the exponent and divide. And then plus c. Now this can be rewritten a little bit. We can clean it up and then we can replace the u with our expression x plus 4 that we started with. So instead of dividing by a fraction, let's multiply by the reciprocal. So that would be 2 times 2 divided by 3, which is going to be 4/3. And I already forgot what our u was. What was it? Oh, it was x plus 4. All right, here we go. X plus 4 to the power of 3/2. And then I would have minus 7, and then instead of dividing by 1/2, let's multiply by the reciprocal of 2 over 1. So it'd be minus 14 of x plus 4 to the power of 1/2. And of course, don't forget your plus c. All right, everybody, that is it. We made it through all 20 questions, and I hope you have that, document that you could print off and follow along with me and all these problems and see my step-by-step solutions. And my goal and hope for you is that you have increased your confidence with U-substitution. All right, provide any comments below if you have any questions or thoughts about how you solve problems differently, and give this video a like if you found it helpful. All right, everybody, that's it for now, and we'll see you in the next video. Bye.